So this lesson is different than all the other lessons because this lesson is called Retrosynthesis, and it is a strategy. There's no new content in this class. It's just a way to help you solve problems in organic chemistry. And so we're going to define what is this strategy of retrosynthesis, and then we're going to talk about how to use it to solve multi-step synthesis problems. Multi-step synthesis problems are the hardest types of problems in organic chemistry, but they're also the most fun. They're the most rewarding because they are the types of reactions that involve multiple steps. Okay, so let's take a look at this strategy, which is called retrosynthesis, which is going to help us. And you don't have to use retrosynthesis to solve these problems. At first, when I was taught this method, I did not want to use it because I found it was extremely awkward. But give it a try, see if it works for you. I'm not going to force you to use it. The name retrosynthesis, as it implies, means reverse synthesis. And it is just a strategy where we're going to work backwards from the product to figure out what happened to the starting material. Okay, so let's take a look at an example of a retrosynthesis type problem, and let's do it a one-step problem just to make it easy. Okay, tell me now, if you want, pause the video and try and figure it out. This is a missing reagent problem. So what should go over the arrow to turn this alcohol into a ketone? There's actually several correct answers here. So timer's on now. Pause the video if you want to figure this out yourself, or in 3 seconds I'm going to tell you the answer. Okay, 3 seconds is up. The answer is PCC. We just learned this reaction in the last lesson. It turns an alcohol, a secondary alcohol, into a ketone. The solvent, which is optional, is typically CH2Cl2. There's another reaction that would do the same thing. Can you figure out what the other reaction is that would turn a secondary alcohol into a ketone? I won't spoil that for you, but that's another totally valid answer that you could say as well. And what I want you to notice here is that we have a forward arrow. The forward arrow tells us that we're going to go from starting materials to products with the reagents are over the arrow. Now, I want to compare that to the retrosynthetic arrow. The retrosynthetic arrow lets us work backward. So it says if we have this ketone, how could we make that from an alcohol? Notice how the arrow looks a little different. It has kind of, it's still facing in the forward direction, but it has kind of the more two lines almost. It's like an equal sign with a cap on it. That is called the retrosynthetic arrow. I didn't make this up. And the way you should read it, if you ever see one of those arrows, just read it like this. Can be made from. That's what it means. Notice there's no reagents shown over the arrow. It just says this ketone can be made from this alcohol. I know that there is a reaction, specifically this reaction here, that will turn an alcohol into that ketone. All the retrosynthetic arrow says is it helps you plan it out and say, okay, to make my ketone, I could make it from an alcohol. I'm not saying necessarily how I'm going to make it from an alcohol, but I just know that there is a reaction that will allow it. Okay, now this just may seem like pointless. Why wouldn't you just draw the forward arrow? Why bother drawing a backward arrow? Well, you can imagine if you have multiple steps to get to the product from the starting material, it might be helpful to work backward a little bit, to try and work backward till you find the starting material. You know, the best strategy really is to work forward a little bit and then work backward a little bit and try and meet in the middle. You can try that as well. Now, all of this is much easier to understand with real examples. So before I give you some real examples of hard multiple step synthesis problems, I want to give you some food for thought, some things to consider. So we'll just say some considerations. You want to look for certain things in the course of your reaction. Some things in your reaction. So number one thing you want to look for is that some functional groups are dead ends. Generally, these functional groups are put in last via SN1 and SN2. Okay. What are some dead-end groups? If you see these groups, they don't do anything. So if they're in your molecule, they were probably put in right at the end, and they were probably put in with an SN2 reaction. So these groups, if you see them in your product molecule that you're trying to make, your target molecule, these are your dead-end groups. OAC doesn't do anything. CN, usually put in with an SN2 reaction, doesn't do anything. N3, we don't know any reactions that do anything to an N3 group. Sulfide, like a sulfur connected to some carbon. Ether, an oxygen connected to some carbon, is pretty much a dead end. An amine or a fluorine, these groups, they don't do anything. They're not good leaving groups. They just kind of do nothing. So if you see them in your molecule, put those in last. So if you see one of these, working backward, replace it with a leaving group. Like bromine, iodine, or tosylate. That's just a few examples of good leaving groups. Because in order to install one of these groups, you need to do SN1 or SN2. Well, in order to install one of these groups, you need to be able to do have a leaving group in order to do SN1 and SN2. So for example, if you saw your target molecule as this, if you saw your target molecule was that, you would identify, okay, that F is a dead-end group. That F is a dead-end group. So I don't know what my original starting material is going to be, but I know right before that F is there, there's a leaving group there, and it's probably looking something like this. Now, there could be more steps before, right? But the last step is going to be installing that fluorine with an SN2 reaction, so we're going to replace that fluorine with a bromine or some other leaving group moving backward. Just an example. Again, much easier to see when I give you a real problem example, which I have not done yet. I'm just sort of blabbing. Okay, next thing I want you to look for is, was carbon added? When you're doing a multi-step synthesis problem, you want to check to see if carbon was added to your starting material. Count the carbons in your starting material. If there's more carbons than you started with, you probably added a carbon-carbon bond. And there are extremely limited ways to make carbon-carbon bonds. One way that you can add a carbon-carbon bond is via SN2, and these ways are pretty obvious and very niche. So SN2 is one way, and let's take a look at an example of that. Take a look. If we had this bromine going to this compound here, what do we put over the arrow? Again, all of these types of synthesis problems are all about guessing what goes over the arrow, missing reactant problems. Well, count the carbons in the starting material. 1, 2, and then count them in the product. 1, 2, 3. We've added carbon. Maybe it was added via an SN2 reaction. And indeed, if you have a CN group, you already know that's one of your dead-end groups. So that's why we have a leaving group in the starting material. And so we're going to install this with an SN2 reaction. So the missing reactant would be NaCN. So just look for that carbon being added. Another thing to look for maybe okay, looking at this problem here, we have 1, 2 carbons, and then the product 1, 2, 3, 4, 5 carbons. So 3 carbons were added, most likely via an SN2 reaction with a deprotonated alkyne. That would give us the product there. Sorry. Okay, now that is a rare way to make a carbon-carbon bond. The far more likely way to make a carbon-carbon bond, I'll show you on the next page, is with an organometallic reagent. And this is where the retrosynthesis gets a little tricky. Organometallics by far is the more common way to make a carbon-carbon bond. So let's take a look at this reaction here. Okay, looking at this partial reaction, what we can see is that we have 1, 2, 3, 4 carbons in our starting material, but 1, 2, 3, 4, 5, 6 in our product, which means we've added 2 carbons to our original 4. Okay, so what I want you to do is look for new carbons added alpha to an alcohol. In other words, look for an alcohol in your product. We have one here. And then look to see if there were any new carbons added alpha to that alcohol. So remember, we had the 4 carbons here. They're still here. So can you see where the new carbons are? They're added alpha to our alcohol. They're right here. Whenever you see new carbons added alpha to an alcohol, that is evidence of organometallic reaction. So the reagents here would be step 1, ethyl magnesium chloride, for example. In step 2, we need that H2O workup. So if you see evidence of organometallics, so I'll just rewrite that OMs, remove the new carbons, and oxidize alpha carbon moving backward. Okay, these are my tips for retrosynthesis. So now let's do an actual problem. Let's put these rules into play, and I think it'll make a lot of sense. Okay, so synthesize, this would be an example problem. Synthesize means make. This guy from that and that. Okay? And what this means is you need to use these 2 ingredients to make this. And you can use any other reactions you want, but all the carbon in the product has to come from these 2 molecules. Okay, so not obvious. Let's do a retrosynthesis to find out. So we'll start by drawing our desired target molecule, which is this. Oops. This is the desired molecule that they want us to synthesize. Okay, now let's work backward from our desired target molecule. Okay, so we'll draw a retrosynthetic arrow, and the first thing I notice is we have a what? A dead-end group. And what do we do when we have dead-end groups? We replace them with good leaving group, like a tosylate or a bromide or a chloride. So let's go ahead and do that. I think replacing with a tosylate is the best idea. So always just replace a dead-end group with a tosylate, and I'll show you why it's the best idea. Okay, now we have a tosylate. We know that there's a reaction that would turn a tosylate into an acetate group. Does it look like this is more likely to be an SN1 or SN2 reaction moving forward? That's right. It looks to be more likely like an SN1 reaction because this is a tertiary substrate. So SN2 is going to be really challenging on that. Okay, now, what reaction makes a tosylate? Only one reaction we know of makes a tosylate. What reaction makes the tosylate? It's the high-tech method. And the high-tech method turns what into a tosylate? It turns an alcohol into a tosylate. So immediately, once you get the tosylate, turn that into an alcohol because you know that's the only way you know how to make a tosylate. Okay, now we have an alcohol. When you get to the alcohol, look for evidence of organometallics, because remember, organometallic additions make alcohols. And what I can see here, I've got my ketone there in purple, and I've got my alkene there in green. And what I can see is I can kind of see the pieces of these molecules in my current state. I can see the green alkene right there, and I can see the 3 carbons of the acetone right there. Can you see that? And what you want to recognize is that there is a new carbon-carbon bond at that position. So what do? Moving backward, we remove the extra carbon. In this case, we remove the green stuff, and that becomes our organometallic, say, for example, this vinyl lithium. And then we oxidize the purple stuff like that. Because we know that a organometallic only reacts with an aldehyde or ketone to form a new carbon-carbon bond. And again, we're working backward. Okay, great. And look, this is one of our starting materials. So that's one of our starting points. This is not one of our starting materials, but we can make that. Remember, we can make organolithiums from the corresponding halide. Now we're ready. Now that we've planned our synthesis in reverse, we can do our synthesis in a forward direction. This is the fun part. Okay, so we'll start with our alkyl bromide, and we'll treat it with lithium metal. Typically, ether is the solvent. This is where you got to remember all the different reactions. That's going to turn our alkyl bromide into our alkyl lithium. Once you make something, you can use it an infinite number of times in the future. So this is part 1. Now part 2, we'll take our ketone and we'll treat that with the organometallic. So step 1, vinyl lithium. Step 2, we need that H2O workup. Don't forget that. And that's going to give us the new carbon-carbon bond. That's the key step. Next, we're going to turn that alcohol into our tosylate. So for that, we do the high-tech method, which is tosyl chloride and pyridine. And then finally, we need to put in our acetate group. We'll do that with an SN1 reaction. So acetic acid would be perfect for that. We want a nice weak nucleophile that won't try and do SN2. So the SN2 column will be Na, poor nucleophile. E2 will be poor because ACOH's conjugate acid is very, very low, pKa. And then the SN1 column will be good because it's tertiary. It's also even better than that. It's a allylic tertiary. And that's your answer. So this would be your answer. So it may seem a little awkward at first, but working backward can really help you out, especially with the more complicated problems. If you think you can just see it in the forward direction, or you want to try like trial and error or something, be my guest. I'm not going to force you to use retrosynthesis, but it's recommended. Okay, let's do another practice problem. Okay, use the following ingredients to make the desired target product. Methyl bromide plus isopropanol to make tert-butanol. And I'll tell you now, it's 3 steps. Okay, so let's try a retrosynthesis first. Start with our product and work backward from our product. What we can see is that we have new carbon attached, alpha, to an alcohol. So we have an alcohol and we have new carbon attached. So we'll remove that carbon and oxidize our alcohol. So there's the alcohol oxidized plus methyl magnesium bromide. Now this ketone could be made from our corresponding alcohol, which is one of our starting materials. And the methyl magnesium bromide could also be formed with methyl bromide, which is another one of our starting materials. So now we're ready for the forward direction. Step 1, we'll make the Grignard reagent, so methyl bromide. Step 2, we'll take our alcohol and turn that into the ketone. How do we do that? Use a reagent like PCC. Then in the subsequent step, you would add step 1, methyl magnesium bromide, and step 2, H2O. That's going to add a methyl group to our ketone and turn it into an alcohol at the same time. And there we go. Our synthesis is done. All right, I'm going to give you another really hard one, and you can pause the video and try it yourself. But why don't we give this a shot, and then we'll do more practice in class. Okay, here's a really hard example. Okay, you are allowed to use this piece, and this piece. And your target molecule is this. Wow. Okay, pause the video if you want to give this a shot. Otherwise, we're going to do a retrosynthesis starting from that product. Okay, if you're still here, you want to see the answer. Sounds good to me. One of the first things you might want to try and do is highlight each of the starting materials in the product. So for example, like this thing, I'll just highlight this in purple, and I can find this in the product. How many of them appear to have been added to the product? 2. You can tell because there's 2 sulfurs. So there's one of them. And then can you see where the other one is? Yeah, it's over here. I noticed the hydrogen's gone, but we'll worry about that. See, this guy here in blue, I can see those double bonds, 2 of those added as well, here and here. Okay. And then we'll call this one in green. I don't see any oxygens in my product, but I do see the 3 carbons in the middle there. So looks pretty reasonable that those are kind of how the pieces came together. The purple and the blue both connected to the green. All right. So now let's do a backward synthesis. Figure out how to put this thing together. So I'll start by redrawing my product. And remember, the first thing you want to look for are those dead-end groups. Do we have any dead-end groups? Yeah, we do. Those sulfur groups, those sulfides, they're not thiols. Thiol is sulfur with hydrogen. A sulfide is sulfur connected to carbon on both sides, kind of like an ether version of sulfur. And so what I can tell is that these are dead-end groups. So remove dead-end groups because those go on with SN2 and SN1 reactions at the very end. So just replace those with tosylates. Okay? So these are our dead-end groups. So whenever you see dead-end groups in your molecule, remember, if I go back to that page here, one of our dead-end groups are SCH3, which is equivalent to what we have here. We have S carbon. It's not a methyl group, but it's an isopropyl group. It's the same thing. Dead-end group. So we put those on last. We make all the dead-end groups from tosylate. Okay, if you want to try now pausing the video and see if you can go all the way back home to the starting materials, be my guest. If at any point you think you can do it yourself, pause the video and try and finish it off. But okay, if you're still with me, you want more. So let's go back again. Tosylates can only be made from one thing, alcohols. You can't make a tosylate from anything else. So going back one more step, we'll turn our OTSs into OHs. And then here we can see we've got some carbons added, alpha to alcohols. That's organometallics. So remove those carbons and oxidize those alcohols up to the aldehyde or the ketone. In this case, they're aldehydes because there's hydrogens on the ends here. right? Those are these hydrogens right here. I'll draw them in. Hydrogens connect to those carbons. Plus an organometallic. And then that can be made from the corresponding halide. Okay, so now we're ready for the forward synthesis. Here we go. We'll start by making our organometallic. So we'll start with our vinyl bromide. We'll treat that with lithium to make our vinyl lithium. Step 2. Oh yeah, and our double aldehyde here, that could be made from our double alcohol, right? We gotta finish our retrosynthesis there. Okay, so we'll start with our alcohol. And we gotta first turn it into an aldehyde so that we can do the organometallic reaction. So we're gonna treat that with PCC. And the PCC is strong. It will oxidize all the alcohols in the molecule up to the aldehyde. Okay, so there we have our 2 aldehydes. Make sure we don't gain or lose carbons, so count the carbons. 1, 2, 3, 1, 2, 3. We still have 3 carbons. Okay, next up, we're going to add our organometallic that we made in step 1. So step 1, vinyl lithium. Step 2, H2O. That's going to add those carbons to the carbonyl carbon. Okay, now turn those alcohols into tosylates. Tosyl chloride pyridine, it's the high-tech method. Okay, and then now we want to put in our sulfur groups. We can put those in either with SN1 or SN2. Let's do SN2. So we could do SN2 if we use the deprotonated form of our thiol. You can do that. You know, honestly, then you have to do an extra acid-base step to make that. Probably easier just to add the thiol in, and that's going to go in via an SN1 mechanism. I'll show you why that would be SN1. And that's going to lead directly to your product. Which looks like that. Why is this last reaction SN1? Let's take a look at the table. So SN2, E2, SN1, E1. Okay, the SN2 column is fair because it's secondary. The E2 column is poor because the conjugate acid is a protonated thiol, which is -7. And the SN1, E1 column is good. It's upgraded from fair because it's allylic with a neutral nucleophile. So the SN1 column is good. Okay. All right, so that's retrosynthesis and forward synthesis, multi-step synthesis problems. There's a few multi-step synthesis problems on your problem set this week. And also check out the practice midterm. There's one on there as well. All right, bye for now. I hope you enjoyed retrosynthesis. But if you're like me, you probably did not connect with this right off the bat. But with some practice, I promise retrosynthesis is definitely the way to go. Okay, bye for now.